In the hour before sunrise, Venus is the brightest thing in the sky, steadier than any star, white and sharp against the darkness. On the right night, in the right conditions, it is bright enough to cast a faint shadow. It looks like a world at peace. It is not. Venus and Earth began the same way. Same raw material, same region of the solar system, nearly the same size and mass. In the early solar system, they were as close to twins as planets get. Whatever set them on different paths did not have to go the way it did. The difference between them was not guaranteed, and yet one of them became this, a world with oceans, air, and life, and the other became something that should serve as a warning. The surface of Venus is hot enough to melt lead. Its atmosphere presses down with over 90 times the force of Earth's, heavy enough that standing on the surface would feel like being 600 meters underwater. And despite all of that atmosphere, Venus is losing it, continuously, right now. Spacecraft have recorded it directly, particles streaming away from the planet, stripped off by the constant flow of charged particles from the sun. There is nothing to stop it. No shield, no barrier, just an open wound in the atmosphere, bleeding out into space day after day, with nothing to slow it down. This is not ancient history. It is not something that happened and ended. It is happening right now, at this moment, as Venus hangs in the morning sky, looking calm and bright and completely unthreatening. The question is not just what went wrong on Venus. It is why Earth was spared the same fate, and whether that difference is as permanent as we assume. Today, we get into it. Before we go any further, if you enjoy exploring the cosmos with us, a quick like or subscribe goes a long way. It helps us keep making these deep dives for curious minds like yours. It starts with what Venus no longer has. Imagine two clocks set at the same moment, taking in perfect synchrony, built from identical parts, and placed side by side beneath the same light. For a time, they keep the same rhythm. Then, almost imperceptibly, one begins to drift. Not by seconds, not even by minutes, but by a difference so small at first that no observer would notice. We are watching that drift unfold across billions of years, written into two worlds that began as one experiment, both formed roughly 4.5 billion years ago, condensing from the same rotating cloud of gas and dust that surrounded the young sun. The materials were shared, the environment nearly identical, the distances close enough that early conditions should have aligned. Venus emerged at about 95% of Earth's diameter and roughly 81% of its mass, composed of similar silicate rock and metal, orbiting just slightly closer to the same star. At the beginning, neither world resembled anything we would recognize today. Their surfaces were molten oceans of rock, their skies thick with steam and volcanic gases, their crusts constantly reshaped by impacts from leftover debris. For perhaps 100 million years, both planets existed in this violent equilibrium, radiating heat into space, while new heat surged upward from their interiors. Gradually, cooling began to win. On Earth, that cooling crossed a threshold. Water vapor condensed into liquid oceans, forming a stable reservoir that could regulate temperature. The crust fractured into moving plates, a process we call plate tectonics, where sections of the surface slowly shift and recycle material back into the interior. Beneath it all, a churning liquid iron core generated a magnetic field, an invisible shield that shaped everything above it. From these conditions, life eventually emerged. But Venus did not follow the same path. It cooled, yes, but into a state that diverged in ways we are still trying to resolve. The timing of that divergence remains one of the most contested problems in planetary science. There is no single moment preserved like a timestamp, only clues. Two leading explanations compete for that turning point. One suggests that Venus's magnetic field either never fully formed or collapsed early, leaving its atmosphere exposed to the sun's influence from the beginning. The other points to a later internal upheaval, a catastrophic release of heat through widespread volcanism that altered the planet's surface and atmosphere, pushing it into a runaway greenhouse state where heat could no longer escape. But which came first, the loss of the magnetic shield or the rise of the greenhouse? The order matters. If the field failed first, the atmosphere may have been stripped gradually over immense spans of time. If the greenhouse took hold first, it may have reshaped the interior itself, shutting down the processes that could have sustained a magnetic field. We are left with a question that threads through everything that follows, not just what happened, but when and in what sequence. Each possibility redraws the entire history of Venus, and with it, our understanding of how similar beginnings can lead to profoundly different ends. Before anything touches a planet, it has already begun its journey at the sun, leaving the surface not as light, but as a steady outflow of matter. You can think of it as breath, though far more relentless. This outward stream is called the solar wind, a continuous flow of charged particles that never stops, never pauses, and never weakens to zero. It moves fast, between 400 and 800 kilometers per second, depending on solar conditions. These particles are mostly protons and electrons, with a smaller fraction of helium nuclei, all carrying electric charge. That charge matters. It means they do not travel blindly, but are guided and shaped by magnetic fields carried with them from the sun itself. At the distance of Venus, this stream takes roughly 4 minutes to arrive after leaving the solar surface. That is the timescale between cause and effect, between emission and impact. At Earth, the same journey takes closer to 8 minutes, giving a slightly longer buffer, though the difference is small in cosmic terms. The wind is always arriving, but the solar wind is not just a stream of particles. It carries embedded magnetic field lines, stretched outward through the solar system. This structure is known as the interplanetary magnetic field, which means the sun's magnetic influence extended across space. These invisible lines act like guides, directing how charged particles move and interact when they encounter obstacles. When this flow meets a planet, the result depends entirely on what stands in its way. There is no universal outcome. Each planet responds according to its own internal structure, its own history, its own defenses, or lack of them. Earth presents a barrier. Deep beneath its surface, liquid iron moves in complex patterns, generating a global magnetic field. This field extends far into space, forming a region called the magnetosphere, which means a magnetic bubble surrounding the planet. Incoming solar wind particles are deflected around this bubble, forced to flow past rather than through it. The atmosphere remains largely protected. But Venus offers no such resistance. There is no intrinsic magnetic field rising from its interior. No global shield extends outward to meet the incoming stream. The solar wind does not bend or divert. It continues forward until it reaches the upper layers of the atmosphere itself. Here, the interaction begins directly. Charged particles collide with atmospheric gases, transferring energy and momentum. The sun's magnetic field lines thread through this region, connecting the flow of space directly to the material of the planet. The boundary between space and atmosphere becomes blurred, active, and unstable. This is not a gentle process. It is continuous, physical contact between a moving plasma and a stationary atmosphere. Over time, it leads to the removal of atmospheric particles, not in bursts, but in a steady extraction that never fully stops. But to understand how this removal works, we need to look deeper, not at the wind, but at what is missing within Venus itself. Far below any surface we could stand on, beyond rock and pressure, there is motion that cannot be seen, but can be measured by its effects. On Earth, that hidden motion shapes everything above it. It begins in the outer core, a vast layer of liquid iron about 2,300 kilometers thick, where heat rises from deeper regions and drives slow circulating currents. These currents are not random. They move in organized patterns because the planet rotates. The rotation introduces what physicists call the Coriolis effect, a force that causes moving fluids to curve and align into large, stable loops. When electrically conductive liquid like iron flows in these patterns, it generates a magnetic field through a process known as electromagnetic induction, which means moving charges create magnetism. This system is called a dynamo. It is not a machine, but it behaves like one. Heat flows outward, fluid moves, rotation shapes the motion, and a magnetic field emerges as a consequence. It sustains itself as long as the conditions remain balanced. Venus, by all measurements we have, should possess similar ingredients. Its density indicates a large iron core, likely comparable in size to Earth's, and its bulk composition suggests the same fundamental materials. There is no reason to assume the core is absent. The structure is there, but the field is not. Every spacecraft that has passed Venus, from early flybys to more recent orbiters, has searched for a global magnetic signature. None has been found. There are weak local interactions, but nothing resembling a planet-wide shield. The dynamo, if it ever existed, is either silent or gone. This absence forces a set of possibilities. One is that the core has cooled and solidified completely, removing the fluid motion required to sustain the process. Without liquid movement, there is no generation of magnetic fields. But this idea struggles against other evidence. Venus shows signs of geological activity that imply internal heat is still present. Another explanation focuses on rotation. Venus turns extremely slowly, completing one rotation in about 243 Earth days. With such a sluggish spin, the Coriolis effect becomes weak. Fluid motions may still occur, but they lack the organization needed to form stable, large-scale currents. Without that structure, the dynamo cannot maintain itself. This is currently the most widely supported view. But there is a third possibility, more complex and more unsettling. At some point between 300 and 500 million years ago, Venus experienced a global resurfacing event, a period when vast amounts of lava flooded the planet and replaced most of its crust. Such an event would have altered how heat escaped from the interior, potentially disrupting the convection currents within the core itself. If that disruption was severe enough, it could have stalled the dynamo, not gradually, but abruptly, on geological timescales. A functioning magnetic field may have existed before this event, shielding the atmosphere and shaping the planet's evolution. Then it stopped. We are left considering a world that may have crossed a threshold where internal dynamics shifted just enough to silence the field entirely. A small change with irreversible consequences. But if the dynamo failed, the timing becomes everything. When that change occurred determines how long the atmosphere stood unprotected and how the process we are measuring today truly began. We begin not with oceans, but with a ratio, a small imbalance hidden within the air that still surrounds the planet. It is measured in atoms, not landscapes, yet it holds the memory of everything that is missing. Scientists call it the deuterium to hydrogen ratio, often shortened to D to H, a comparison between two forms of the simplest element. Hydrogen usually exists as a single proton with one electron. Deuterium is different. It carries an extra neutron, making it heavier, more resistant to escape when energy tries to push it away. This difference seems minor, but over immense spans of time, it becomes decisive. On Venus, this ratio is about 150 times higher than what we observe on Earth. That is not a fluctuation, it is a signature of loss. When hydrogen escapes into space, the lighter version leaves more easily, while the heavier deuterium lingers behind. Slowly, the balance shifts. The atmosphere becomes enriched in what cannot leave as quickly. This enrichment allows us to work backward. If we know how much deuterium remains and how it accumulates relative to hydrogen loss, we can estimate how much hydrogen must have escaped. And hydrogen, in this context, points directly to water. Each molecule of water contains two hydrogen atoms. Remove the hydrogen, and the water is effectively gone. The numbers suggest a past that feels distant from what we see now. Venus once held enough water to form shallow coverage across its surface, at least several meters deep, possibly far more. Some climate models extend this further, proposing oceans tens or even hundreds of meters deep, stable for periods approaching 2 billion years. Conditions may have allowed it. A study published in 2019 by NASA researchers modeled early Venus under different atmospheric and rotational scenarios. The results indicated surface temperatures below 50 degrees Celsius for extended intervals, warm but within the range where liquid water can persist. Clouds would have formed differently, reflecting sunlight in ways that moderated heating, but that state did not last. The elevated D to H ratio tells us the loss was not sudden. There was no single moment when oceans vanished. Instead, hydrogen escaped gradually, molecule by molecule, over hundreds of millions, perhaps billions of years. Water was broken apart, its components separated and removed at different rates, leaving only a chemical trace behind. We are not looking at a dried basin or an exposed shoreline. We are reading a record written into the composition of the atmosphere itself, a record that cannot be erased by resurfacing or buried under rock. It persists because it is statistical, built from countless individual losses accumulating into a measurable pattern. But the ratio alone does not explain the mechanism. It tells us what was lost and how it accumulated over time, not the precise process that tore water molecules apart and carried their components away. To understand that, we have to follow the interaction between sunlight, charged particles, and the upper atmosphere, where the transformation begins. High above the cloud tops, where the atmosphere thins into space, sunlight does more than illuminate. It alters matter. You are looking at a region where energy arrives in its most direct form and where even stable molecules begin to break apart under constant exposure. Ultraviolet radiation, often shortened to UV, carries enough energy to disrupt chemical bonds. When these photons strike molecules, like carbon dioxide, or the last traces of water-related compounds, they split them into smaller pieces. Electrons are stripped away in the process, leaving behind ions, which are atoms or molecules that carry an electric charge. This change is critical. Neutral particles drift without much influence, but ions respond immediately to magnetic fields. Their motion becomes guided, shaped, and accelerated by invisible structures that fill the space around the planet. The upper atmosphere becomes a region of charged particles, suspended and ready to interact. But the magnetic field controlling this region does not belong to Venus. It arrives embedded within the solar wind, carried outward from the sun as part of the interplanetary magnetic field. When this field encounters the cloud of ions surrounding Venus, it does not pass through unchanged. It connects. The field lines thread into the ionized gas. linking the movement of solar particles to the material of the atmosphere itself. This interaction sets the stage for a process known as ion pickup. The term describes exactly what happens. Charged particles from the atmosphere are caught by the moving magnetic field and dragged along with it. Once attached, they are no longer bound to the planet in the same way. They are accelerated outward, gaining speed until they match the flow of the solar wind. That speed can reach several hundred kilometers per second. At those velocities, escape is not a question. The particles are carried away, removed from the planet's influence, and dispersed into interplanetary space. The process is continuous, repeating for each ion that forms in the upper atmosphere. We have measured this directly. The European Space Agency's Venus Express mission, operating from 2006 to 2014, carried an instrument called Aspira 4. Its purpose was to detect and analyze escaping particles, identifying their composition and velocity with precision. The results revealed a pattern. Oxygen and hydrogen were leaving the planet in a ratio of roughly 1 to 2. For every oxygen atom lost, 2 hydrogen atoms accompanied it. This proportion is not arbitrary. It matches the chemical structure of water, where each molecule contains 2 hydrogen atoms bonded to 1 oxygen atom. What we are observing is not random loss. It is the systematic removal of the building blocks of water, carried away in the same proportions that once formed liquid reservoirs. Even though no standing water remains, the process continues, driven by the same physics. But this creates a strange continuity. The atmosphere is losing something that no longer exists in bulk form, a lingering signature of a past state preserved only in chemistry. Each escaping ion represents a fragment of that history, lifted away and scattered into space, one interaction at a time. Count the scars on a world, and you can estimate how long its surface has been left undisturbed. On most solid bodies, time writes itself in impacts, each collision leaving a crater that persists unless something erases it. The Moon preserves this record in overwhelming detail, its surface layered with billions of years of strikes, each one still visible. Venus should follow the same logic. Given its size and location, it should carry tens of thousands of craters accumulated over its history. But when we map its surface, we find fewer than 1,000. The discrepancy is not small. It is a signal that something has removed the evidence. The pattern deepens the mystery. The craters that do exist are scattered almost randomly, without clustering into older regions or thinning into younger ones. On a planet with a long, continuous surface history, you would expect variation, areas with more impacts, areas with fewer, reflecting different ages. Venus shows no such gradient. This uniformity leads to a stark conclusion. Nearly the entire surface must have been renewed within a relatively narrow window of time, not in pieces, not gradually, but on a global scale, a reset. By measuring how many craters have formed since that event, scientists estimate the timing. The numbers point to a period between 300 and 500 million years ago. Before that, whatever surface existed has been almost entirely erased, buried beneath newer material. The leading explanation is global volcanic resurfacing. This does not describe isolated eruptions or regional flows. It refers to a period when vast volumes of molten rock rose from the mantle and spread across the planet, covering previous terrain in layer after layer of lava. The scale is difficult to compare, exceeding anything seen on Earth in recorded geological history. The cause lies in how Venus handles internal heat. Without plate tectonics, the slow recycling system that allows Earth to release heat gradually, Venus lacks a steady outlet. Heat accumulates within the mantle, increasing pressure over immense spans of time. Eventually, that pressure reaches a threshold where the system can no longer contain it. When release comes, it is not subtle. The mantle partially melts, and magma forces its way upward across wide regions. Instead of isolated volcanic chains, the process becomes widespread, flooding plains, reshaping highlands, and creating the large shield volcanoes that dominate the surface today. The tesserae, the deformed highland regions, may be among the few remnants that predate this event. What we see now is the aftermath of that interval, a surface largely formed in one prolonged episode of geological upheaval. It appears relatively young because it is not in planetary terms, but in comparison to the age of the planet itself. But such an event would not have been limited to the surface. Altering the flow of heat through the mantle would have affected the deeper interior as well, potentially changing the conditions that sustain or suppress internal motion. If a magnetic field existed before this period, the disruption could have been enough to weaken or extinguish it. The consequences extend beyond geology. They connect directly to the processes that continue above, shaping how the planet interacts with its environment and how it continues to change over time. A signal arrives from a place no human will ever stand, carried across millions of kilometers, fragile and brief. It is not a voice, not a clear image at first, but a transmission pushed through heat and pressure, fading even as it is received. For a short time, we were there. The Soviet Venera program began in 1961, an effort that would continue for over 2 decades. 16 spacecraft were sent toward Venus, each designed to descend through an atmosphere known to be hostile, though its full severity was only gradually revealed. With each mission, the design changed, adapting to conditions that exceeded expectations. The challenge was not a single hazard, but several acting together. The pressure at the surface is about 90 times that of Earth, enough to crush conventional structures. Temperatures reach around 465 degrees Celsius, hot enough to weaken metals. The atmosphere itself contains corrosive compounds that degrade exposed materials. Survival required resisting all of this at once. The solution resembled a deep-sea vessel. Each lander was built as a sealed, spherical pressure chamber constructed from thick metal to withstand compression. Layers of insulation slowed the transfer of heat inward. Inside, cooling systems worked continuously, not to maintain comfort, but to delay failure. Time was the only objective. Venera 7, landing in December 1970, achieved the first success. It transmitted data from the surface of another planet for 23 minutes before its systems ceased. That brief window confirmed surface conditions directly, transforming speculation into measurement. Subsequent missions extended that window. Venera 9 and 10, arriving in 1975, returned the first images from the surface. The photographs revealed a landscape of fractured, dark rocks scattered across flat terrain, illuminated by a dim orange light filtered through the thick atmosphere. There were no shadows of clouds passing, no signs of erosion as we know it, only a stillness shaped by extreme conditions. The longest survival came with Venera 13 in March 1982. It remained operational for 127 minutes. During that time, it transmitted color images and recorded sound. The audio, later analyzed, captured a low, continuous rumble a combination of wind and the constant force of dense air pressing against the lander's structure. These missions did more than confirm conditions. They revealed the character of the surface itself. The rocks appeared relatively unweathered, lacking the accumulation of dust or the layered erosion seen on older terrains elsewhere. This supported the idea that the surface had been renewed on a large scale in the geological past, leaving behind a landscape that had not been exposed for billions of years. But the landers were limited by their environment. Their instruments were designed for immediate surroundings, for pressure, temperature, and composition at the surface. They could not observe the processes unfolding high above, where particles escape and interactions with space occur continuously. We were present for minutes. The processes that define the planet unfold across spans far longer, beyond the reach of those brief transmissions. There is a boundary above Venus that does not belong to the planet alone. It forms and dissolves continuously, shaped by forces arriving from the sun rather than rising from within. You would not see it with your eyes. Yet it determines how much of the atmosphere survives each passing moment. At high altitudes, sunlight transforms the upper layers into a charged environment. Ultraviolet radiation strips electrons from atoms and molecules, creating a region filled with ions and free electrons. This region is called the ionosphere, which simply means a layer of ionized gas capable of conducting electricity. All planets with atmospheres develop an ionosphere, but here it becomes something more important. It becomes the only interface between the atmosphere and the solar wind. There is no deeper magnetic structure to take over, no internal field to push outward and define a stable boundary. When the solar wind arrives, carrying its embedded magnetic field, it interacts directly with this ionized layer. The moving plasma cannot pass through unchanged. Instead, it slows, compresses, and bends around the planet. In doing so, it generates a magnetic structure of its own. This is called an induced magnetosphere. The term means the magnetic field is not produced by the planet itself, but created through interaction with the external flow. It exists because the solar wind meets a conductive medium and is forced to respond. The difference from Earth is profound. Earth's magnetosphere originates from its interior, anchored deep within the core, extending tens of thousands of kilometers into space. It is stable, persistent, and largely independent of short-term solar variations. Venus's induced field is the opposite. It is shallow, variable, and entirely dependent on the incoming conditions. On quieter days, this improvised shield performs better than expected. Measurements from the Venus Express mission showed that a significant portion of the solar wind is diverted around the planet. The ionosphere, interacting with the external field, creates a buffer that reduces direct impact. It is not complete protection, but it slows the process. But the sun is not always quiet. At irregular intervals, the sun releases large bursts of plasma known as coronal mass ejections. These events send dense, fast-moving clouds of charged particles into space. When one of these reaches Venus, the balance changes immediately. The increased pressure compresses the induced magnetosphere, pushing it closer to the planet. In some observed cases, the compression is so extreme that the protective region nearly disappears. The boundary collapses inward, and the solar wind gains direct access to the upper atmosphere. During these periods, the rate at which particles escape increases dramatically, sometimes by factors of 10 to 100 compared to normal conditions. The shield does not fail completely, but it is overwhelmed. It recovers after the event passes, rebuilding itself from the same interaction that formed it. This cycle repeats. shaped by the variability of the sunday. What exists here is not a permanent defense, but a delay mechanism. It stretches the timescale of loss from millions of years to billions, altering the pace but not the outcome. And within this shifting boundary, something else was observed, a pattern emerging near the poles that does not behave like the rest. Above the southern pole, something rotates that you would never see from the surface. It is not a storm of clouds or wind, but a structure made of charged particles moving in a slow, continuous spiral. Instruments aboard Venus Express revealed it not as a brief event, but as a stable feature, present every time the region was observed. This structure is a vortex, a rotating flow of ionized particles being drawn upward and away from the planet. It forms because of how the solar wind interacts with the induced magnetic environment surrounding Venus. The geometry of that interaction shapes where particles can move and where they are guided. As the solar wind approaches, it is partially diverted around the planet. The flow splits and curves, moving along the boundary of the induced magnetosphere. But on the side facing away from the sun, called the night side, these diverted magnetic field lines do not remain separate. They reconnect, linking together and stretching outward into space. This extended region is known as a magnetotail, a long structure trailing behind the planet, aligned with the direction of the solar wind. Within this tail, conditions allow charged particles to be accelerated. Ions originating from the upper atmosphere are pulled into this region and guided along the magnetic field lines. The south polar vortex marks the connection point. It is where the magnetotail links back to the atmosphere, creating a focused pathway through which ions can escape. Instead of drifting randomly, particles are drawn into this rotating funnel, gaining energy as they move outward. This is not a rare occurrence. Measurements showed the vortex is continuous, present across multiple observations and stable over time. It represents a persistent route of loss, a defined channel through which atmospheric material is removed. The northern hemisphere behaves differently. There, the escape pattern is less organized, lacking the same clear rotational structure. This asymmetry arises from the orientation of the interplanetary magnetic field relative to Venus. The direction of the incoming field influences how and where reconnection occurs, shaping the flow unevenly across the planet. As a result, the loss of atmosphere is not uniform. It varies with location and direction, concentrated in specific regions rather than spread evenly. The planet sheds material more efficiently through these structured pathways, feeding into the magnetotail that extends behind it. If you could observe Venus from far beyond the solar system, you might detect a faint extension trailing from it, not composed of dust like a comet, but of ionized gas gradually dispersing into space. It would be subtle, almost invisible, but it would be there. This escaping material is not arbitrary. The composition of the ions being carried away reflects the chemistry of what once existed in greater abundance. By examining what leaves, we gain insight into what was once present in forms that are no longer visible. Sometimes the present reveals itself through the past, hidden in data that waited decades for the right tools to be understood. In 2023, researchers returned to radar images collected more than 30 years earlier by NASA's Magellan spacecraft, which had mapped Venus between 1990 and 1994. What they found was not static. The focus was a volcanic region known as Mont, the largest volcano on Venus, rising several kilometers above the surrounding plains. Magellan had imaged this area multiple times, capturing subtle variations in radar reflections that correspond to changes in surface structure. By comparing two images taken 8 months apart in 1991, scientists noticed something unexpected. The shape of a volcanic vent had changed. In February of that year, the vent covered about 2.2 square kilometers, with steep walls and a relatively narrow opening. By October, the same feature had expanded to nearly 4 square kilometers. Its geometry had altered, the interior appearing partially filled, consistent with the presence of fresh lava. The transformation could not be explained by measurement error or imaging artifacts. This was direct evidence of an eruption. For decades, the question had remained open. Was Venus still geologically active, or were all visible features remnants of ancient processes long concluded? The Magellan data, re-examined with modern analysis techniques, provided the first clear answer. Activity continues. But the discovery did not stand alone. Separate teams analyzing thermal signatures in the same data set identified anomalies consistent with relatively recent lava flows at multiple locations across the planet. These findings suggest that volcanism is not confined to a single site, but distributed, ongoing, and varied in intensity. This changes how we understand the interior. A geologically active surface requires heat, not just residual warmth, but sufficient energy to drive melting and movement within the mantle. Venus is not a cooling relic, it is still dynamic beneath its surface. But this introduces a tension. If the interior remains hot enough to sustain volcanism, why does it not generate a magnetic field? The energy source exists, the fluid motion may exist, yet the field does not. The most consistent explanation returns to rotation. Without sufficient spin, the internal flows may lack the structure required to maintain a coherent dynamo. At the same time, volcanic activity feeds the atmosphere. Gases released from eruptions, particularly sulfur dioxide, rise and contribute to the formation of the planet's cloud layers. These compounds cycle through the atmosphere, participating in chemical reactions that maintain its composition over time. So two processes occur simultaneously. Material is added from below, replenishing parts of the atmosphere, while material is removed from above through interactions with the solar wind. The balance is uneven. Loss continues, driven by external forces, while replenishment depends on internal activity that cannot fully compensate. We are looking at a system still in motion, where the interior and the environment remain connected, influencing each other across scales that range from kilometers to entire planetary systems. From a distance, Venus appears almost uniform, a bright, steady presence that reflects sunlight with unusual efficiency. Its brilliance is not subtle. It outshines every planet in the night sky, second only to the sun and moon. That brightness comes from a global cloud layer that reflects about 70% of the light that reaches it. These clouds form a continuous shell. They begin around 45 kilometers above the surface and extend upward to roughly 70 kilometers. Within this range, visibility ends. No optical instrument can see through them directly. The surface below is hidden not by darkness, but by an unbroken barrier of dense material. But these clouds are not made of water. They consist of droplets of sulfuric acid, a compound formed from sulfur dioxide and water interacting under intense solar radiation. The concentration ranges between 80 and 98%, making them among the most chemically aggressive environments known in the solar system. Any exposed material must resist not only heat and pressure, but constant corrosion. The cloud layer is not still. Winds move through it at speeds approaching 360 kilometers per hour. These are not gusts or temporary flows. They are sustained, global currents that carry the entire cloud system around the planet in about 4 Earth days. This behavior is called atmospheric superrotation, which means the atmosphere rotates much faster than the solid body beneath it. The contrast is extreme. While the surface takes about 243 Earth days to complete a single rotation, the clouds circle it dozens of times in that same period. The mechanisms driving this difference are complex, involving energy transfer, wave patterns, and momentum exchange within the atmosphere. But the clouds do more than move. They participate in ongoing chemical cycles. Sulfur compounds rise from lower layers, react in the presence of sunlight, and form the acid droplets that compose the clouds. These droplets can later break down or settle, returning material downward and continuing the cycle. Within this system, there is an additional layer of uncertainty. Observations show that the cloud tops absorb a significant portion of incoming ultraviolet radiation, roughly half of what arrives. The specific substance responsible for this absorption remains unidentified. It is referred to as the unknown ultraviolet absorber. Several candidates have been proposed. Some involve iron-based compounds, others involve different forms of sulfur, known as allotropes, where the same element exists in multiple structural forms. There is also a more complex possibility involving organic molecules, though no direct confirmation has been made. But regardless of composition, the effect is measurable. The absorption alters how energy is distributed within the atmosphere, influencing temperature, circulation, and chemical reactions. It shapes the system from within. What we see from afar is a reflective surface, smooth and luminous. What exists within it is dynamic, corrosive, and only partially understood. The clouds define how Venus appears to us, but they also conceal processes that continue to operate beneath and within them, beyond direct observation. In September 2020, a faint spectral line appeared where none was expected. It came from radio observations of Venus, analyzed by a team led by Jane Greaves at Cardiff University and published in Nature Astronomy. The signal suggested the presence of a molecule called phosphine. Phosphine is simple in structure. It consists of one phosphorus atom bonded to 3 hydrogen atoms, written chemically as pH3. On Earth, it is rare in natural settings. It is produced either through industrial processes or by biological activity in environments without oxygen, where certain microbes generate it as a byproduct of metabolism. That association carried weight. If phosphine existed in the clouds of Venus, it would require an explanation. Known chemical pathways under Venusian conditions struggle to produce it in significant quantities. The possibility, however remote, was that something unfamiliar, perhaps even biological, might be contributing to its presence. The proposed location of the signal added to the intrigue. It corresponded to altitudes between about 48 and 60 kilometers above the surface. In this region, temperatures range from roughly 0 to 60 degrees Celsius, and pressures fall between about 0.4 and 2 times that of Earth's surface. Compared to conditions below, this layer is relatively moderate. For a brief period, the idea expanded rapidly. Observations were discussed, models were adjusted, and the implications were considered across disciplines. But the signal itself required verification. Within weeks, independent teams began reanalyzing the original data. They examined how the signal had been extracted, how background noise was handled, and how calibration affected the result. The phosphine signature remained detectable, but at a much lower intensity than initially reported. Its significance became uncertain. Further observations followed. Other telescopes, using different methods, searched for the same spectral signature. Some reported no detection at all. Others found signals that could be explained by alternative processes or by limitations in the data itself. The consistency required for confirmation did not emerge. But the episode did not resolve into a simple correction. It exposed something deeper. The chemical environment within Venus's clouds does not fully align with current models. Measurements of various compounds, including oxygen and sulfur species, show distributions that are not easily explained by known reactions alone. The unknown ultraviolet absorber remains unidentified. The balance of certain gases does not match expectations under standard atmospheric chemistry. Each discrepancy is small, but together they form a pattern. What we encountered was not a confirmed discovery, but a boundary. The data pointed to processes that are not yet fully described, occurring within an environment that resists straightforward interpretation. The question that emerged was not only about phosphine, it was about how complete our understanding of this system truly is, and whether the chemistry we observe can be explained entirely by processes we already know. Long before landers survived their brief minutes, a different idea was written down quietly. In 1967, Carl Sagan and Harold Morowitz proposed that life might exist not on the surface of Venus, but within its clouds. At the time, this suggestion stood apart, overshadowed by assumptions that the planet was uniformly hostile. For decades, the idea remained largely dormant. But our understanding of life on Earth has shifted. Over the past 40 years, scientists have studied extremophiles, organisms that thrive in environments once considered uninhabitable. These include microbes that live in sulfuric acid with a pH of 0, but organisms that endure temperatures above 120 degrees Celsius, and species that survive intense radiation or crushing pressure deep beneath the ocean. Each discovery expanded what we consider possible. The cloud layer of Venus, particularly between about 50 and 60 kilometers altitude, falls within ranges of temperature and pressure that are not inherently prohibitive. Temperatures can sit between 0 and 60 degrees Celsius, and pressures remain within levels that many Earth organisms could tolerate. These conditions are not gentle, but they are not beyond all precedent. But there is a limiting factor. It is called water activity, which refers to how much water is available for chemical processes, not just the presence of water molecules, but their accessibility for biological use. In Venus's clouds, water activity is extremely low because the environment is dominated by concentrated sulfuric acid droplets. The water that exists is chemically bound, not freely available. No known organism on Earth can survive under such conditions. But the phrase "no known" has changed before. Boundaries that once seemed absolute have shifted as new forms of life were discovered in unexpected places. The question is not whether current biology allows for it, but whether alternative biochemical strategies could exist. In 2020, planetary scientist Sarah Seeger and her colleagues proposed a model for how such life might persist. The idea describes a cycle within the atmosphere itself. Organisms could exist in the more temperate cloud layers, metabolizing and reproducing while suspended in droplets. Over time, they would sink into lower, hotter regions where conditions become hostile. At that point, they could transition into a dormant state, forming spores that resist desiccation. These spores would then be carried upward again by convective currents, rising back into regions where activity could resume. The cycle would repeat, forming a closed loop entirely within the atmosphere. This is not a claim of discovery. It is a structured hypothesis built to be tested. It outlines specific conditions behaviors, and chemical signatures that future missions could search for. It turns a question into a framework. But if such a system exists, it would be embedded within an environment that is steadily losing material to space. The processes we have been tracing would not only affect gases and ions, but potentially any suspended particles within that flow. The loss would not distinguish between chemistry and biology. It would remove both, at rates defined by external forces rather than internal resilience. Instead of light, we used echoes. In 1990, NASA's Magellan spacecraft entered orbit around Venus and began mapping the surface using synthetic aperture radar, a technique that sends radio waves downward and reconstructs images from the returning signal. This method can penetrate dense cloud cover, allowing us to see terrain that optical instruments cannot access. For 4 years, Magellan scanned the planet, building a detailed map of its surface. What emerged was not just a hidden landscape, but a record of processes unlike those on any other world we have studied. The patterns were clear, yet their origins were not always straightforward. One of the most distinctive features identified was the tesserae. These are highland regions marked by complex, intersecting ridges and fractures, indicating intense deformation. They appear older than the surrounding plains, standing above them both physically and in geological history. Their structure suggests repeated cycles of compression and extension, reshaping the crust over time. If these regions represent remnants of an earlier surface, they may hold chemical signatures from a period before the widespread resurfacing event. Certain minerals form only in the presence of liquid water, and if such minerals are found within tesserae, they would provide direct evidence of past surface conditions that differ significantly from those observed today. Elsewhere, Magellan revealed structures known as coronae. These are large, circular features, some reaching diameters of up to 2,600 kilometers. They form when plumes of hot material rise from the mantle, pushing upward against the crust. The surface domes, fractures, and eventually collapses, leaving a ringed structure surrounded by ridges. More than 500 coronae have been identified across Venus. Their abundance reflects a style of internal activity that is not present on Earth. Here, plate tectonics continuously recycles the surface, erasing large-scale features over time. On Venus, without that mechanism, these structures persist, preserving evidence of mantle dynamics that would otherwise be lost. Another class of formations, called arachnoids, appears as networks of radial fractures extending outward from central points. They resemble webs, with lines spreading in multiple directions across the surface. These features likely result from localized upwelling of material, creating stress patterns that propagate outward through the crust. Together, these observations describe a planet that underwent a massive transformation and then entered a relatively stable phase. The surface bears the imprint of widespread volcanic and tectonic activity, followed by a period of limited change. It is not static, but the large-scale structure has remained largely intact since that earlier interval. The map is comprehensive, but not complete in interpretation. Some features resist simple classification, and the relationships between different regions are still being studied. The data provides detail, but not all answers. Future missions aim to refine this picture. A planned descent probe will target tesserae regions directly, analyzing their composition during descent. If specific mineral signatures are detected, they will extend the timeline of conditions that once existed, linking surface structure to atmospheric history through measurable evidence. If we pause the motion and measure it, the process resolves into numbers, small at first, almost negligible on human scales. Yet those numbers accumulate without interruption, second after second, across spans that dwarf any timeline we can intuitively grasp. Data from the Venus Express mission provided the first precise measurements of atmospheric escape at another planet. Using the Aspera 4 instrument, which detects charged particles and their energies, scientists quantified how much material leaves Venus under different conditions. The results transformed a qualitative idea into something exact. Under relatively calm solar conditions, the planet loses about 300 grams of oxygen every second. Alongside that, between 500 and 1,000 grams of hydrogen escape in the same interval. Combined, this amounts to roughly 1 to 2 kilograms of atmosphere lost per second. Over a single day, that becomes close to 100 tons. But the Sun does not maintain a constant output. During periods of increased activity, especially when coronal mass ejections pass through the inner solar system, these rates rise sharply. Venus Express recorded events where atmospheric loss increased by factors of 10 to 100. For a short time, the steady outflow becomes significantly more intense. These variations matter when extended over geological time, since the large-scale resurfacing event, estimated to have occurred between 300 and 500 million years ago, Venus has likely lost an amount of material equivalent to a global ocean several meters deep. This estimate emerges from integrating measured rates over that duration, accounting for fluctuations in solar activity. But there is a scale mismatch that reshapes how we interpret this process. The current atmosphere of Venus has a mass of approximately 4.8 times 10 to the 20th kilograms. That is about 93 times the mass of Earth's atmosphere. Against that total, a loss of 1 to 2 kilograms per second is extremely small. At current rates, it would take hundreds of billions of years to remove the entire atmosphere through ion escape alone. So the process is not rapid. It does not lead to sudden collapse or near-term disappearance. The atmosphere is stable in the sense that it persists, even as it is continuously diminished. The change is measurable, but not immediate. But the future alters this balance. The Sun is not constant over long periods. Its luminosity increases gradually as it ages, and with that increase comes stronger ultraviolet radiation and a more energetic solar wind. Both of these factors enhance the mechanisms that drive atmospheric escape. The rates we measure today are not fixed. They are part of a trend. Over hundreds of millions to billions of years, this trend becomes significant. The slow loss we observe now may accelerate, not abruptly, but steadily, changing the long-term evolution of the atmosphere. We are observing a process that unfolds on timescales far beyond human experience. It proceeds quietly, continuously, with no single moment marking its progress. Yet every second contributes, adding to a cumulative change that defines the planet's trajectory over time. We tend to imagine the Sun as constant, a steady source of light that defines the background of everything else. But it is not fixed. It changes slowly, almost imperceptibly on human timescales, yet decisively across billions of years. What we see today is only one moment in a long progression. About 4.5 billion years ago, the young Sun emitted roughly 70% of the energy it does now. The remaining 30% has been added gradually as nuclear reactions in its core continue to convert hydrogen into helium. This process increases the core temperature, which in turn increases the overall brightness of the star. The implications extend outward. For Earth, this creates a known problem. If the Sun was dimmer in the past, The planet should have been frozen, yet geological evidence shows the presence of liquid water early in Earth's history. This contradiction is called the faint young sun paradox, and it is explained by higher concentrations of greenhouse gases trapping more heat in the atmosphere. But Venus faced a different threshold. As solar output increased, the balance between incoming and outgoing energy shifted. At some point, the conditions crossed a boundary where heat retention became self-reinforcing. Once that threshold is exceeded, cooling mechanisms no longer compensate and temperatures rise in a sustained way. Venus appears to have passed this point earlier in its history. But brightness is only part of the change. A more luminous sun also produces stronger ultraviolet radiation and a more energetic solar wind. Ultraviolet photons carry the energy required to break molecular bonds, particularly in compounds containing hydrogen. As the intensity of this radiation increases, the rate at which molecules are split in the upper atmosphere also increases. This directly affects atmospheric escape. The measurements we have today from missions like Venus Express capture current conditions. They show how particles are lost under present solar output. But those conditions are not representative of the entire past. 2 billion years ago, the ultraviolet intensity was lower and the solar wind less energetic. The processes we observe now have been strengthening over time. This means the rate of loss has not been constant. It has been increasing gradually, following the evolution of the sun itself. The present moment is part of a larger trajectory, one that continues forward. Looking ahead, models of stellar evolution indicate that the sun will become about 10% brighter in approximately 1 billion years. That increase is enough to shift conditions on Earth as well. As temperatures rise, the oceans begin to evaporate, introducing water vapor into the upper atmosphere, where it becomes vulnerable to the same processes that affected Venus. The mechanisms are already understood. Ultraviolet radiation breaks apart water molecules, hydrogen escapes, oxygen remains or reacts, and the cycle repeats. Over long periods, the loss becomes irreversible. The difference between Earth and Venus is not the nature of the process, but the timing. What we observe on Venus is not an anomaly. It is a stage in planetary evolution that depends on distance, composition, and time. Place the three inner worlds side by side, and a pattern begins to emerge, not in their surfaces alone, but in the outcomes they represent. Each formed from similar material within the same region, under the influence of the same star. Yet each arrived at a different state, shaped by subtle differences that grew over time. Mars provides the first contrast. It is smaller, with less mass to retain internal heat. That difference set its evolution on a faster path. As the planet cooled, its core lost the energy needed to sustain motion. Without movement, there is no dynamo. And without a dynamo, there is no global magnetic field. This transition occurred around 4 billion years ago, early in its history. Once the field disappeared, the atmosphere became exposed. The same processes we have traced elsewhere began to operate there as well. The solar wind interacted directly with the upper layers, gradually removing particles and reducing pressure over time. What was once a thicker atmosphere, capable of supporting liquid water, diminished. Today, Mars retains only a thin layer of carbon dioxide, with surface pressure less than 1% of Earth's. Measurements from NASA's MAVEN mission show that the planet continues to lose atmosphere at a rate of about 100 grams per second. The mechanism is consistent, but the scale has changed. There is little left to remove. But the cause is clear. Mars lost its protection because it cooled too quickly. Venus followed a different path. Its size allowed it to retain internal heat, and evidence suggests that energy still drives geological activity beneath the surface. But rotation introduces another requirement. Without sufficient spin, the internal motion cannot organize into the patterns needed to sustain a magnetic field. The conditions for a dynamo are present, but not aligned. So the outcome is similar. No field, direct exposure. Earth occupies a narrow middle ground. Its mass is sufficient to maintain internal heat over long periods, and its rotation is fast enough to structure that motion into a functioning dynamo. At the same time, its surface is divided into moving plates, allowing heat and material to cycle between the interior and the atmosphere. This process regulates carbon dioxide levels, maintaining conditions that support liquid water. Each factor contributes: size, rotation, and tectonics. Remove any one of them, and the balance shifts. A smaller Earth would cool faster, approaching the state of Mars. A slower rotation would disrupt the dynamo, leading toward conditions seen on Venus. Without plate tectonics, carbon would accumulate in the atmosphere, altering the thermal balance. The differences are not dramatic in isolation. They are variations within a shared framework, but their effects compound over time, leading to distinct outcomes that persist. What we see is not a single template repeated, but three variations on the same initial conditions. The solar system did not produce one inevitable result. It produced multiple possibilities, each determined by a combination of factors that interact in complex ways. When we search for life beyond our system, we begin with distance, not composition, not history, but orbit. The concept is called the habitable zone, which means the range around a star where temperatures allow liquid water to exist on a planet's surface under suitable conditions. It is a useful starting point. Since the early 2000s, this definition has guided the classification of exoplanets. If a rocky world orbits within this zone, it is marked as a candidate for habitability. The assumption is simple. With the right temperature, water can remain stable, and where water is stable, life may follow. But there is a problem. Venus sits within this same zone around our own star, according to most definitions used in current models. Its orbit falls well inside the region where liquid water could, in principle, exist. By distance alone, it qualifies. Now imagine observing our system from 40 light-years away. With present detection methods, you would measure size, orbit, and perhaps atmospheric composition in broad terms. Venus would appear similar in mass and radius to Earth, orbiting within the habitable zone. It would be flagged as promising. But the reality is very different. The surface temperature exceeds 460 degrees Celsius. The atmosphere is dense and chemically aggressive. Any liquid water that may have existed is no longer present in stable form. The conditions we have documented are incompatible with surface life as we understand it. This mismatch led to the definition of the Venus zone, a term introduced in 2013 by planetary scientists Stephen Kane and Giada Arni. It describes a region closer to a star where planets may appear habitable by distance, yet are more likely to resemble Venus, with runaway greenhouse conditions dominating their evolution. This reframes how we interpret data. Among the thousands of rocky exoplanets identified so far, many fall within distances comparable to Venus rather than Earth. They are cataloged as potentially habitable based on orbital position, but we lack critical information. We cannot directly measure their magnetic fields, determine their rotation rates with precision, or assess the dynamics of their interiors. These factors matter. They influence whether a planet can sustain a stable atmosphere, regulate its temperature, and resist long-term loss processes. Without them, distance alone becomes an incomplete indicator. A planet may sit in the right location, yet evolve along a path that leads away from habitability. Venus demonstrates this clearly. It shares key physical properties with Earth, yet diverged in outcome. This suggests that similar planets elsewhere may follow comparable trajectories. The default state for rocky worlds in habitable zones may not be Earth-like, but Venus-like, shaped by processes that push them beyond the limits of surface stability. This possibility changes the expectation. The number of truly Earth-like planets may be smaller than initial estimates suggested, not because they do not form, but because maintaining those conditions requires a combination of factors that may not often align. If you could stand within the atmosphere, somewhere between crushing depth and empty space, the stillness we imagine would dissolve into motion. The clouds above would not drift gently. They would race, circling the planet again and again, driven by forces that do not resemble familiar weather systems. Within those clouds, electrical activity occurs. The first hints came from the Venera landers. Their instruments recorded sudden disturbances, bursts of electromagnetic interference that could not be explained by mechanical noise. These signals suggested lightning, though confirmation required independent measurement. That confirmation arrived later, when Venus Express detected electromagnetic signatures consistent with lightning discharges directly from orbit. But how often does it happen? The answer remains uncertain. Some analyses indicate lightning may occur as frequently as on Earth, or even more often, distributed across the global cloud layer. Others suggest it is rare, appearing only under specific conditions. The data supports both interpretations, depending on how it is processed and which signals are emphasized. Regardless of frequency, the presence of lightning carries consequences. Electrical discharges introduce energy into the atmosphere in short, intense bursts. This energy can drive chemical reactions that would not occur under normal conditions, breaking apart molecules and allowing new combinations to form. In an environment already rich in reactive compounds, these processes can alter composition in ways that are still being studied. But the atmosphere is not uniform. Below the main cloud deck, between about 30 and 45 kilometers altitude, there is a region where the air becomes clearer. Light can pass through more easily, and the sky would appear deep orange rather than opaque. This layer sits beneath the densest clouds but above the extreme pressures closer to the surface. Above it lies the tropopause, a boundary around 65 kilometers altitude that separates different atmospheric regimes. It marks a transition in temperature and circulation, defining where certain processes dominate over others. Closer to the surface, conditions change again. Despite the intense motion higher up, winds near the ground move slowly, typically 1 to 2 meters per second. But speed alone does not determine force. The density of the atmosphere means even slow-moving air carries significant momentum, exerting pressure that would be felt strongly by any object. This creates a contrast that is not fully understood. High above, the atmosphere moves rapidly, completing a rotation in just a few days. Near the surface, motion is subdued, yet the energy driving the upper layers must originate somewhere and be transferred through the system. At the poles, additional structures form. Large, rotating vortices dominate each region, spanning areas comparable to continents. These are not related to the escape processes observed elsewhere, but they contribute to the overall circulation adding complexity to a system that already resists simple description. What appears smooth from a distance is, in detail, layered, active, and uneven, shaped by interactions that occur across altitude, chemistry, and motion simultaneously. Consider altering a planet not by observing it, but by intervening in its chemistry and energy balance. The question is simple to ask. Could Venus be changed into something more like Earth? The answers, when examined through physics, become precise very quickly. One of the most discussed approaches involves introducing hydrogen into the atmosphere. The idea relies on a basic chemical reaction. Hydrogen can combine with carbon dioxide to form water and solid carbon, often in the form of graphite. If carried out at planetary scale, this reaction would reduce atmospheric carbon dioxide, lower pressure, and produce water simultaneously. But the scale defines the challenge. To meaningfully alter the atmosphere, the required hydrogen mass is on the order of 4 times 10 to the 19th kilograms. That amount corresponds roughly to an asteroid about 600 kilometers in diameter. Acquiring, transporting, and distributing that mass exceeds any current or near-future capability. The reaction itself is understood. The logistics are not. Another proposal shifts the focus away from the surface. Jeffrey Landis at NASA suggested building floating habitats within the cloud layer, around 50 kilometers above the surface. At that altitude, temperature and pressure fall within ranges that are comparatively moderate. The environment remains harsh, but not immediately destructive to engineered systems. These habitats would use the surrounding atmosphere to their advantage. A breathable mixture of nitrogen and oxygen is less dense than carbon dioxide, providing natural buoyancy. Structures could float without continuous propulsion, supported by the density difference. Solar energy is abundant at that altitude, offering a consistent power source. This approach does not transform the planet, it adapts to it. But both concepts encounter a deeper constraint. Even if the atmosphere were altered, even if conditions at the surface became more stable, the absence of a magnetic field would remain. Without that protection, interactions with the solar wind would continue, gradually removing atmospheric particles over long periods. To address this, some proposals extend beyond the planet itself. One idea involves placing a large magnetic dipole at the Venus-Sun L1 Lagrange point, a location where gravitational forces allow an object to remain relatively stable between the planet and the sunday. A dipole is a magnetic source with 2 poles, like a bar magnet, and positioned correctly, it could deflect incoming solar wind before it reaches the planet. A study published in 2017 involving researchers, including Sonny White, explored this concept. The physics suggests it is feasible. A sufficiently strong magnetic field placed upstream could create a protective region around Venus, reducing atmospheric loss. But feasibility does not imply practicality. The scale of such a structure, the energy required to maintain it, and the materials needed to construct it place it far beyond current technological limits. These are not engineering problems we can solve incrementally. They require capabilities that do not yet exist. What remains is a distinction. Transforming Venus is not ruled out by physics. The processes are understood, the reactions predictable. But the magnitude of intervention required places it outside the reach of present civilization, extending into timescales measured in thousands of years and resources drawn from across the solar system. We rarely think of other planets in terms of sound. Images arrive first, measurements follow, but sound requires something more, a medium dense enough to carry vibrations and an instrument capable of surviving long enough to record them. For a brief period, that condition was met. In March 1982, Venera 13 transmitted audio from the surface for 127 minutes. It remains the only direct recording from another planet's surface during that era of exploration. The signal was faint, shaped by interference and limitations in the equipment, but it carried something unmistakable: a continuous, low-frequency rumble. When researchers reanalyzed the recording using modern techniques, they identified multiple contributing sources. The dominant component appears to be the pressure of the atmosphere itself, nearly 90 times that of Earth, pressing against the lander's structure. That force produces subtle mechanical responses, small shifts and stresses within the hull that translate into sound. There are other elements. Wind moves across the surface. Though slowly in speed, it carries significant momentum due to the density of the air. As it interacts with the lander, it generates additional vibrations. The combined effect is not a sharp or dramatic noise, but a persistent, enveloping presence, a background that does not fade. But the way sound travels there differs from what we experience. In 2021, researchers at NASA's Jet Propulsion Laboratory used acoustic modeling to simulate how sound propagates through the Venusian atmosphere. They found that sound waves would travel at about 410 meters per second compared to roughly 343 meters per second on Earth. The increased speed results from the density and composition of the atmosphere. This changes how sound is perceived. Lower frequency sounds, often described as bass, travel more efficiently. The thick atmosphere conducts these vibrations with less loss, allowing them to persist and propagate over longer distances. Higher frequencies, in contrast, are absorbed more readily, diminishing as they travel. A thunderclap on Venus would arrive faster and carry deeper tones. Human speech, if it could be produced under such conditions, would be altered. The resonance of the voice would shift, emphasizing lower harmonics while higher components fade. Words would still form, but their texture would change, shaped by the medium through which they move. Sound becomes a tool. Future mission concepts include deploying seismometers and microphones to capture vibrations from the ground itself. These instruments could detect internal activity, subtle movements within the crust, or deeper layers, transmitted as acoustic signals. By analyzing how these signals travel, scientists could infer properties of the interior, much like medical imaging reveals structure within the human body. What we have now is limited, a short recording from a single location, captured under extreme constraints. But even that fragment offers a direct connection, a sense of presence defined not by sight, but by vibration. There's a quiet moment before an answer arrives, when decades of uncertainty compress into a narrow window of expectation. We are standing inside that moment now, with multiple missions aligned toward a single destination. 3 major projects, developed independently, are converging on Venus within the same decade. Each carries a different instrument set, a different approach, and a different piece of the larger question. Together, they form something closer to a coordinated investigation than any previous attempt. NASA's Davonsci mission, short for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry and Imaging, will send a descent probe through the atmosphere over roughly 63 minutes. As it falls, it will sample gases at carefully selected altitudes, measuring composition with a precision never achieved before on Venus. Among its targets are noble gases, chemically inert elements like argon and xenon that preserve ancient planetary history. Their ratios act as a record, revealing whether large volumes of water once existed and later escaped. As the probe approaches the surface, it will image the Tesserae highlands in detail. These fractured terrains may be remnants of older crust, possibly recording conditions that predate the catastrophic resurfacing event described earlier. The images will not simply show terrain, they may show memory. But descent alone cannot map a planet. NASA's Veritas mission, an orbiter named for Venus emissivity, radio science, INSAR, topography, and spectroscopy, will circle the planet and construct high-resolution maps using radar capable of penetrating the cloud cover. With a resolution of about 15 meters, it will reveal surface features with clarity comparable to terrestrial mapping satellites. It will identify active volcanic regions, measure surface deformation, and track changes over time, allowing scientists to determine whether the planet is still reshaping itself. Another orbiter will arrive with a different focus. The European Space Agency's Envision mission will combine radar mapping with subsurface probing, using signals that penetrate below the surface to reveal internal structure. By analyzing how these signals reflect and scatter, scientists can infer whether the core remains liquid or has solidified. This is the most direct test yet of the dynamo question, the question that shaped everything that followed. But there is another path being considered. A privately proposed mission, often called Venus Life Finder, aims to enter the cloud layers directly and search for complex organic chemistry. Designed by a team including Sarah Seeger, it would target the unexplained chemical anomalies already observed, including the ultraviolet absorber and the debated phosphine signal. It is a focused search, not for certainty, but for evidence that something unaccounted for is present. Each mission answers a different part of the same story. Core state, surface history, atmospheric chemistry, possible biology. But together, they converge on a set of questions that have remained open since the first flyby in 1962. Did Venus ever hold oceans? Does its interior still move? Are its processes purely chemical, or something more complex? We are no longer guessing. Long before we understood our own climate in detail, we were forced to solve another world first, a hotter one that refused simple explanation. In trying to describe that alien atmosphere, we built the tools that now describe our own. The equations came first. During the 1960s and 70s, researchers working with early probe data needed a framework to explain surface temperatures high enough to melt lead. They refined the concept of the runaway greenhouse effect, a state where heat becomes trapped faster than it can escape, driving temperatures upward without balance. This was not abstract theory. It was required to explain real measurements. But those same equations did not stay isolated. They migrated. Scientists like Carl Sagan treated planetary atmospheres as variations on a shared system, governed by radiation, chemistry, and circulation. By adjusting initial conditions, such as solar input or atmospheric composition, the same mathematical structure could describe multiple worlds. The contrast between outcomes made the framework stronger, not weaker. Venus clarified the extremes. Once models could reproduce its conditions, they could be scaled downward to Earth, where the greenhouse effect operates in a far more moderate regime. Climate modeling on Earth inherited this lineage directly, including radiative transfer, the process describing how energy moves through gases and clouds. Every modern climate simulation still depends on those foundations. But the exchange did not stop at temperature. When spacecraft revealed that Venus loses atmosphere through ion pickup, a process where charged particles are carried away by solar wind, it provided a working example of atmospheric escape without a magnetic field. That mechanism became essential in understanding Mars, where similar loss had already stripped much of its air. Comparative planetology, the study of planets through comparison, gained its first clear structure from this link. One world informed another. Atmospheric motion added another layer. Venus rotates slowly, yet its upper atmosphere races around the planet in just 4 Earth days. This phenomenon, called superrotation, means winds move many times faster than the surface below. Models built to explain this extreme circulation are now applied to exoplanets, especially those locked to their stars, where one side always faces the light. Venus became a benchmark. It defined how far atmospheric behavior could stretch while remaining physically consistent. That matters when we interpret distant worlds, where only faint signals reach us. But perhaps its most important contribution is a boundary. By demonstrating a fully realized runaway greenhouse state, Venus sets the inner edge of the habitable zone, the distance from a star where liquid water can persist. Without this example, estimates would remain speculative. With it, we have a clear limit, anchored in observation. The implications extend quietly. Every Earth-observing satellite, every projection of future warming, carries assumptions tested against that distant planet. The temperature of 465 degrees Celsius is not just a number. It is a constraint, a warning, and a calibration point all at once. We learned by contrast. Venus did not simply diverge. It revealed what happens when familiar processes cross invisible thresholds. And in mapping those thresholds, we learned where our own world still stands. Imagine placing a meter on a process that never pauses, then watching the numbers change while nothing visible seems to move. That is how this knowledge arrives, quietly, with instruments counting what the eye cannot follow. Most cosmic events sit beyond our sense of time. Stars evolve over billions of years, their changes recorded only in comparison across generations of observers. Galaxies drift and merge on scales that erase any direct human witness. Even on Earth, mountains rise and erode so slowly that we understand them through layers, not moments. But here, something different unfolds. We have measured particles leaving a planet in real time, tracked as streams of charged atoms escaping into space. Instruments have recorded loss rates in kilograms per second, not as estimates, but as continuous data. The process does not wait for interpretation. It is happening now. This changes how we know it. Reconstructed history carries distance, a sense that the event has already resolved. Direct observation removes that distance. It places you inside the process, even if the timescale remains vast. The difference is subtle, but it shifts perception. You are not imagining a past ocean disappearing. You are watching its remnants leave, atom by atom, carried away by forces already described. The solar wind passes at hundreds of kilometers per second, interacting with the upper atmosphere, lifting ions, accelerating them, releasing them into interplanetary space. This is not occasional. It is constant. But the pace resists intuition. At roughly 1 to 2 kilograms per second, the loss is measurable, yet slow, relative to the planet's total mass. No visible change marks the passing of a day or even a century. The transformation stretches across hundreds of millions of years, a duration that does not fit naturally within human concern. So a question forms, almost unavoidable. Can we care about a process that will never complete within any human lifetime? The difficulty lies not in the science, but in scale. Human attention is shaped by immediacy, by events that unfold within years or decades. Venus asks for a different kind of awareness, one that extends across deep time without losing coherence. It asks whether understanding alone can sustain concern. But this is not only about another world. The same categories of change exist here, unfolding at their own measured pace. The sun continues to brighten over geological time, increasing the energy delivered to Earth. Plate tectonics, the slow cycling of the crust, will not persist forever. Magnetic fields can weaken, strengthen, or fail, depending on internal dynamics. These are not immediate threats. They are processes already underway, moving along trajectories defined by physics rather than intention. Venus provides a visible case, one where the outcome is clearer because the system crossed a threshold long ago. We observe and we calculate, and in doing so, we confront a scale of change that does not wait for us to notice, yet becomes undeniable once measured. For most of our history, knowledge began with the naked eye, and the sky offered only light, motion, and pattern. Venus was one of the brightest points, steady and unyielding, revealing nothing beyond its glow. We tracked it carefully. Ancient observers recorded its cycles with precision, noting its appearances before sunrise and after sunset, mapping its path over decades. These records carried meaning, guiding calendars and shaping belief systems, yet the object itself remained hidden behind its brightness. Even with telescopes, the mystery persisted. When Galileo resolved its phases in the early 17th century, he confirmed its orbit around the sun, but not its nature. The surface stayed concealed, the atmosphere impenetrable to visible light. The planet remained a question without an answer. But that changed within a single human lifetime. In 1962, a spacecraft passed close enough to measure temperature and radiation directly. The data contradicted every expectation of a mild world. It revealed conditions far beyond anything imagined, forcing a complete revision of how we understood that point of light. From that moment, the process accelerated. Subsequent missions mapped the surface, sampled the atmosphere, and recorded interactions with the solar wind. Piece by piece, the unknown became structured knowledge. Not complete, not final, but coherent enough to describe the system in detail. We now know what it is. A planet similar in size and composition to Earth, yet transformed by processes that drove it beyond stability. Its atmosphere, its surface, its internal dynamics, all measurable within defined limits. The transformation is no longer speculative, it is observed. This creates a strange position. We are the first generation to hold this understanding in full, to see Venus not as a symbol or an abstraction, but as a physical system with a history and a trajectory. Every human before the space age looked at the same object without access to this layer of reality. The contrast is absolute. Where there was once only brightness, there is now temperature, pressure, chemistry, motion. Where there was once interpretation, there is measurement. The transition happened quickly, compressed into decades rather than centuries. But the deeper shift is quieter. We have extended perception beyond natural limits, building instruments capable of detecting individual ions escaping from a distant atmosphere. We have measured velocities, densities, and interactions occurring far beyond direct human reach. This is not passive observation. It is constructed awareness, and it places us in an unusual moment. In the 4.5 billion year history of the solar system, Venus has undergone its transformation without any known observer capable of understanding it. Only now has a species developed the tools to perceive the process in detail, to quantify it, and to place it within a broader framework. We arrived late, but not too late to see. That timing carries weight, even if it is difficult to define. We exist at a point where the system can be understood, yet still continues, unfolding according to the same laws that shaped it from the beginning. We are watching, and we know that we are watching. Take two nearly identical systems, then shift one variable at a time, and the differences begin to speak. This is how we read Venus now, not as an isolated world, but as a comparison that reveals what remains hidden at home. Every measurement carries a reflection. When we track atmospheric escape there, we refine how gases behave under radiation and magnetic influence here. When we model circulation under extreme heat, we sharpen the limits of our own climate system. The data does not travel directly, but its structure does. But the mirror is not static. Earth itself is changing, slowly, measurably, within the same physical framework. Over roughly the past 170 years, observations indicate a reduction in magnetic field strength of about 9%. This decline may be part of a natural reversal cycle, a process where the field flips polarity over thousands of years, yet the present trend remains observable. A magnetic field is not permanent. It depends on motion within the outer core, a layer of liquid iron moving under the influence of heat and rotation. If that motion alters, the field responds. If it weakens, the interaction with solar wind shifts, changing how the atmosphere is shielded. But shielding is only one part. Deep within the planet, plate tectonics continues to move crustal plates, recycling carbon through subduction where one plate sinks beneath another. This process regulates atmospheric carbon dioxide, preventing accumulation over long periods. It acts as a stabilizing loop, linking geology to climate. That loop has a lifespan. As internal heat gradually dissipates over billions of years, the energy driving tectonic motion decreases. Models suggest that within 1 to 2 billion years, tectonic activity could slow significantly. Without that movement, the recycling process weakens. Carbon begins to accumulate. Volcanic outgassing continues to release carbon dioxide, but without efficient removal, the balance shifts. Atmospheric concentration rises, trapping more heat. Surface temperatures increase, altering oceans, altering chemistry, altering feedback systems that currently maintain stability. This progression is not abrupt. It unfolds over timescales far beyond human experience, measured in hundreds of millions of years. Civilizations rise and fall within intervals, too small to register against it. Yet the direction is defined by physics, not speculation. But inevitability does not mean immediacy. The difference matters. A billion years is approximately 200 times longer than complex multicellular life has existed on Earth. The process is real, but distant, unfolding without urgency from a human perspective. Still, the comparison remains. Venus represents a later stage, a system that crossed thresholds Earth has not yet reached. The mechanisms are the same, but the timing differs. One planet shows the trajectory, the other remains earlier along the path. We are not separate from that trajectory. We are observing it from within, using another world as reference. The mirror does not predict exact outcomes, but it outlines possibilities constrained by shared laws. And so the image resolves. Not identical, not immediate, but connected, a reflection stretched across time, where one planet shows what the other has not yet become. Picture a shoreline that no instrument will ever photograph, a boundary between liquid and rock that existed for spans of time longer than our species has existed. We cannot see it, yet the conditions that allow it are written into the chemistry we have already measured. For up to 2 billion years, models suggest liquid water could have persisted on Venus. That duration exceeds the interval between Earth's first stable oceans and the emergence of complex multicellular life. It is enough time for cycles to establish, for chemistry to repeat, for patterns to deepen beyond randomness. There would have been tides, though driven only by the Sunday. Without a large moon, the oscillations would be weaker, but still present, creating rhythmic movement along shallow margins. Energy gradients, differences in temperature and chemistry, would have existed wherever water met volcanic rock. Hydrothermal systems likely formed. At the seafloor, heated fluids rising through cracks could have created localized environments rich in dissolved minerals. On Earth, such systems support complex chemical reactions, forming organic molecules from simpler compounds. The same processes require no biology to begin. Lightning would have contributed. Electrical discharges through a dense atmosphere can break apart molecules and recombine them into more complex structures. This mechanism, demonstrated in laboratory conditions, operates wherever the right gases and energy are present. The ingredients were there: water, energy, chemistry, time. These are the same components that shaped early Earth. Whether they cross the threshold into biology on Venus remains unknown. But the record is gone. Any surface evidence that might have preserved that history was buried during the global resurfacing event, covered by extensive lava flows and altered by extreme conditions that followed. What remains at the surface today reflects a later chapter, not the earlier one. The window did not close suddenly. There was no single impact, no abrupt external disruption. Instead, internal and external factors shifted gradually. The sun brightened over time, increasing the energy input. Internal heat dynamics altered atmospheric composition. Water began to break apart under ultraviolet radiation, its hydrogen escaping to space. Loss accumulated. Oceans diminished, not in a single event, but through persistent processes operating over immense durations. Each step followed directly from physical laws, without deviation, without intent. But what makes this difficult to hold is the absence of drama. There is no singular moment to point to, no event that defines the transition. Conditions simply crossed thresholds, one after another, until liquid water could no longer remain stable at the surface. Physics continued. The same processes that allow complexity to emerge can also remove the conditions that sustain it. There is no preference in that direction, only consistency. We cannot reconstruct the details. We do not know the appearance of those waters, their depth, their chemistry beyond broad estimates. We do not know if anything ever moved within them. That uncertainty is not temporary, it is likely permanent. And so we are left with a possibility. A long interval where conditions allowed something to begin, followed by a longer interval where those conditions no longer existed, with no preserved record bridging the two. A window is defined not only by what it allows, but by how long it remains open. That is the quiet framework Venus brings into focus, a constraint that sits beneath every measurement we have taken. Habitability is not permanent. It is a condition sustained by balance, maintained only while multiple processes align within narrow limits. Energy input, atmospheric composition, internal heat, magnetic shielding, all must remain within ranges that permit liquid water to exist over time. But those ranges shift. Stars evolve, brightening gradually as nuclear fusion alters their internal structure. Planetary interiors cool, changing the dynamics that drive magnetic fields and tectonic motion. Atmospheres respond, adjusting composition through chemical and physical feedback. Each system carries a timeline. The duration of that timeline depends on initial conditions, mass, rotation, orbital distance, and countless interactions between them. Some planets lose stability quickly. Others maintain it for billions of years. None remain unchanged indefinitely. Earth's window opened long ago, roughly 4 billion years in the past, conditions allowed stable oceans to form. Within a few 100 million years, simple life emerged. Complexity followed much later, and intelligence appeared only in the most recent fraction of that span. The sequence is not guaranteed. On this planet alone, the fossil record shows multiple mass extinctions, events where large fractions of life disappeared in relatively short intervals. Each reset altered the path forward, and none ensured the eventual outcome. But timing matters. We exist during a period where conditions remain stable enough to support complex ecosystems, yet not so far along that increasing solar luminosity has disrupted that stability. It is a narrow interval relative to the full lifespan of the planet. This is where Venus reframes the picture. If a similar world experienced a comparable window, one that remained open for hundreds of millions or even billions of years, and then closed without producing a system capable of observation, that history would leave little trace beyond chemical signatures. The possibility extends outward. Across the galaxy, countless planets may pass through similar phases, reaching conditions suitable for liquid water, sustaining them for extended periods, then losing them as internal or stellar evolution progresses. But how many of those windows produce observers? The question cannot be answered directly. We can estimate probabilities, model evolutionary pathways, and compare planetary systems, but the emergence of intelligence depends on sequences that may be rare, contingent, or both. Venus does not provide the answer. It provides the context that makes the question unavoidable. It shows that suitable conditions can exist and then disappear through ordinary processes without external disruption, without any requirement for sudden catastrophe. We are inside one such window. We observe another that has already closed. The comparison defines the boundary within which our own existence sits, not as a constant state, but as a phase within a larger progression. And that framing changes the scale of what it means to observe at all. Step outside before sunrise, or wait just after sunset, and let your eyes settle on the brightest point that is not the moon. It does not flicker. It holds steady, pale, and unmistakable, a fixed presence in a sky that slowly turns. You have seen it before. Every human who has ever lived under open sky has seen that same light, rising and setting in cycles that repeat with quiet precision. It was tracked, named, woven into stories and calendars, always present, always unexplained. For most of that time, it meant beauty. The brightness suggested something pure, something elevated, something worth reverence. Without instruments, without data, appearance was the only guide. The name that endured reflects that interpretation. But knowledge changed the meaning. We now understand that the brightness comes from thick clouds of sulfuric acid, reflecting most of the sunlight that reaches them. Beneath those clouds lies a surface shaped by heat and pressure, a system defined by processes we have measured in detail. The light remains the same. The interpretation has shifted completely. What once suggested perfection now reveals transformation, a trajectory that carried a familiar world into conditions far beyond stability. Yet the appearance still holds a kind of resonance, not because it is gentle, but because it represents a system that came close to a different outcome. The conditions that once allowed liquid water, the time available for complex chemistry, all of it existed within a finite window. But the window did not remain open. The processes described across this journey continue without interruption. The solar wind flows outward from the sun at hundreds of kilometers per second, interacting with the upper atmosphere, removing particles steadily. Each day, roughly 100 tons of atmospheric material are lost to space. This continues. Not for years, not for centuries, but for spans that extend into hundreds of millions of years, while the sun itself gradually increases in brightness. The system evolves without awareness, following physical laws that do not pause. Nothing on that planet registers the change. There is no observer within the system to measure, to interpret, or to record. The transformation proceeds, regardless of whether it is understood. But there is an observer nearby. On another planet, within the same system, matter organized into structures capable of building instruments, detecting particles, measuring fields, and constructing explanations. Those instruments were directed outward, toward that bright point. We learned to read what was happening. We identified past conditions through chemical signatures, measured ongoing loss through direct observation, and connected those processes into a coherent description. The understanding is incomplete, but it is real. It does not alter the outcome there. The processes on that world will continue as they would have without observation. No measurement changes the trajectory. No model reverses it. But something else has occurred. Within the same system, a place emerged where the process could be seen, described, and understood. That capacity did not exist for most of the system's history. It exists now. And that changes the meaning of the light you see.